All right. Last thing to take a look at. This is going to be a crash course, no pun intended, for calculus. Let's say that we've got the following equation. Position as a function of time. Now, x usually means your horizontal position, and t definitely usually represents your time. So what I'm going to do is the following. Oh, I apologize. Let me introduce one other thing that we absolutely need. We have a series of definitions. Our velocity as a function of time, but velocity in general is defined. I use an equal sign with one little extra line. That means this is the definition of it. It's the derivative of my position with respect to time. This is dx, so we have position versus time in an infinitely small interval of time. Now, in the one that I showed a moment ago, there was a distance integral. That's one thing that you have to keep track of in physics. We take measurements of the rate of change depending on if it's with time or with position or with all sorts of stuff. That's why I prefer this notation. Many of you may start off where you'll learn something along the lines of that the speed or the velocity is the position prime, where you'll put a little apostrophe up there for a derivative. Please, please, please get past that very quickly. I didn't want to convert to this notation because it's so much extra work writing, but trust me, there is no better notation that I'm aware of than this. Do not use the apostrophe when you're dealing with a physics context. We take derivatives and we need to know with respect to what. Also, our acceleration, usually as a function of time, is defined to be the derivative with respect to time of the velocity, but that also means that it is d squared dt squared. That's another notation. These two 2's mean that we take two derivatives. All right, my class or my period that I have to film this video in is rapidly coming to an end. So let's take a look real quick at a little bit of kinematics, and then I'll put the other video together for you for deriving some of our kinematic equations. So let's say that we have a position as a function of time. Let's say that it is 3t squared. Quick and easy way to do derivatives, and this will cover the vast majority of the derivatives that we need to do in class. You've got this variable is equal to the stuff that you're working with. In our case, it's going to be x and t, so the one on top and then the one on bottom here. We're taking the derivative with respect to t, and that means wherever we see a t, we're going to do the following. We're going to take t, and we're going to take this number and take it down to one less than whatever it was. But we're also going to then take whatever number is here, 3 times the original number. Basically, the way we usually describe it is you bring the 2 down here, and then this becomes 2 minus 1. My derivative of this will be equal to 2 times 3 is 6. That number came down here, and we have 2 minus 1 times t raised to the 1, which is just t. So, if I were to take the derivative of this, the derivative with respect to time, I'll end up with 6t. If this is my position as a function of time, this is my velocity. My velocity as a function of time equals 6t. How fast am I going at t equals 0? I plug in 0. It's not moving at all. How fast am I going at 1 second? It is going 6 meters per second. You're welcome to double check this with some of your kinematic equations as well. All right, we can also then take this and turn it into the acceleration as a function of time by once again taking the derivative with respect to time. I take the derivative of my velocity, so another way of writing this would be d vt dt equals, and I take the derivative of this. Well, this is 6t to the 1. I bring the 1 down, so 1 times 6. And then this goes to 1 minus 1, which is 0. So I end up with the following, which is 6 times 1, 6 times t raised to the 0. T raised to the 0, anything raised to 0 is just 1. My acceleration is 6. In this case, I'm leaving out my units, 6 meters per second squared. In fact, this one is one that our kinematic equations that I've given you in class will work on because our acceleration is constant. So you're welcome to go through and double check this. Say at time equals 0, find out where you're at. Well, we're at a position of 0. At time equals 1, 1 squared times 3, we're at a position of 3. Okay, so we start at, or our delta x will be 3 meters for the very beginning, so delta x is equal to 3. Our initial velocity is 0, our final velocity is whatever you'd like, and then find the acceleration, or whatever you'd like. At 1 second, it would be 6 meters per second. So if you plug in the values, remember delta x is going to be x1 minus x0, final minus initial. That would be 3 meters minus 0 meters. We can also plug in that v of time 1, v1, that's where I get that notation from. We plug in 1 into this equation, 6t, and we end up with, 6t, we end up with 6 meters per second. V initial, we plug in 0, we end up with 0 meters per second. And let's say that we're trying to find the acceleration using our kinematic equations. Well, I don't have and don't want time, so we would use v final squared equals v initial squared plus 2a delta x, okay? Well, v final squared would be 6 meters per second quantity squared, so that's 36 meters squared per second squared equals 0 plus 2 times a times 3 meters. Okay, so I divide to get a by itself. I'm going to divide by 6. That'll get rid of the 2 and the 3. Divide this by 6, and we find that a, our acceleration, according to our kinematic equations, is 6 meters per second squared, which is exactly what we got with the calculus. Great. This is a rundown on how to take a derivative. You basically take this term, do this where the number comes down, and you do the number minus 1. If you have multiple terms, let's say that we have x as a function of t is equal to 3t squared plus 2t plus 6. Let's have a more complicated one. When you take the derivative, you can actually take the derivative of each of the little steps. So we would then end up with, our velocity would be 2 comes down, 2 multiplies with 3, so we get 6t. 2 minus 1 is just to the 1, so that's 6t, plus 1 comes down, and then we have 1 minus 0, so 2 times 1 is 2, plus, well, this is weird. There's no t there. What do I do? Well, you can imagine that this is actually t to the 0. This is t to the 1, that's t to the 2. Well, 0 comes down, and I would have 6 times 0. That may not actually be the best way of doing it, because then you'll end up with 1 over t. Well, even still, 0 comes down, so I'd have 0 times 6 times t raised to the negative 1, you could say. But it doesn't matter because all of it is multiplied by 0, and you end up with 0. The derivative of a constant is 0. The other way to keep track of that is, way back up here, remember a derivative tells you the rate of change. If you have a constant, that means your graph looks like this. That's a constant. The rate of change of that is, well, 0. It doesn't change. I can change my delta x as much as I want, and my y never changes. My slope of this is 0. Whenever you have a constant, 6, the derivative of it will be 0. All right, we'll pick up with more of that later. Okay, so continuing a little bit with calculus. We've been talking at length about kind of the ideas behind it, how to use it. Again, if you've been through a calculus class, the last little bit of what I talked about and what I'm about to talk about is probably going to be, hopefully, old news for you. Let's do one other thing with taking a derivative. Now, normally, let's say that we had a function that looked like this, y equals 18x squared plus 4x plus 6. Many times they teach you by default that when you take a derivative, you would do y prime equals and then some stuff. Please, please, please do not use this notation. What we're going to do is we're going to take the derivative of this function with respect to x, ddx of y. Since this is y, we'll be taking the derivative of this thing with respect to x. That means x is our variable, and we'll be working with that. Now, you all probably won't have to deal with multivariable calculus, but in physics, you want to make certain that you're taking the correct derivative. Some things are time derivatives, some are spatial derivatives. There are all sorts of different types of derivatives. You won't have to worry about multivariable calculus, but you do need to be cognizant that derivative doesn't just mean magically derivative. It's derivative with respect to something. This is with respect to x. You can have a derivative with respect to time. Those are important in the actual real-world applications of that. All right, so I won't use y prime. Prime in physics carries kind of a different meaning. I'm going to use the notation that I much prefer, and I recommend you do, d dx of y. That would be dy dx, which is taking the derivative, much like we saw before. It's finding this, shrinking our slope down to an interval that gets infinitely thin, where we have dx and dy, where d implies that it's infinitely thin. Basically, that's the understanding of it, and then you kick into high gear with just the robotically solved thing. Well, if I'm going to do that, we know that dy dx will be equal to, well, the 2 comes down, 18 times 2 is what, 36x, and then that's 2 minus 1, so we leave that as 1, plus, the 1 comes down, 4x plus, well, that's a constant, the derivative of that is going to be 0. So we end up with our derivative, dy dx, or d dx of y, equals 36x plus 4. We could then take a second derivative, and we'd end up with 36. I should be careful, a second derivative with respect to x. All right, so that's how you apply this in just using the day-to-day how to work with the equations. Here's where we're going to start looking at the opposite of this, integration. All right, let's take the one that I just put together. We know that we have a new function that I'm going to call not y prime, which is what I'd normally call it. We're instead going to call it q. Why not? Q is my dy dx, and it is equal to 36x plus 4. All right? Well, actually, we don't necessarily need to call it q. In fact, let's call it what we had before. It is dy dx. Let's say that I want to find the original equation. In this case, we could say q is equal to the derivative with respect to x of our function y. Okay? In short, what I'm trying to do is I want to undo that. I'm not going to, so basically there was a derivative relationship. I want to find out what y was based on this. Now, many of you may be saying, just go back to the previous slide. Yes, that's because we already know the answer. We're going to double check it. And we're going to do that by doing an integral, which will kind of go the opposite direction of the derivative. It's the one that finds the area under the curve. So I'm going to show you how to do that. This q equals 36x plus 4, and I know that it is equal to dy dx. Why is that important? We'll see in a moment when I get a few other things set up for you, but let's see how to work with this. So we have dy dx equals 36x plus 4. I'm going to undo what I just did, but here's where things are going to get a little bit strange. If you're a calculus professor, what I'm about to do will result in you being filled with unholy fire and anger. And if you're not a calculus professor, then what I'm about to do is pretty much just what you do. You can almost pretend that this is a fraction. It's not really, but remember, we got it by looking at slopes, rise over run, although things get a little bit trickier than that when you start making things infinitely small. But for our purposes, we should be able to do this pretty much every single time. What we can do is, I can multiply by dx. But whatever I do to one side, I need to do to the other side. And I need to multiply the entire side, as it were, by dx. What we're actually doing, this technique is called separation of variables. Separation. I'm bad at spelling. Words are hard. Anyway, separation of variables. It's the number one thing that we'll actually be doing in physics to use calculus to derive what we're looking for, or some equations. Separation, that's definitely an O, but I can't remember if that's an E or an A or what's what. Anyway, words are hard. The important thing is this. I'm going to go ahead and get this out of the way, because math professors would, at least so far as I know, agree that we can treat this as though it were a fraction, even though it's not. But we can do this mathematically if the function y is something called a well-behaved function. And basically what that means, well-behaved, means the following. It's a couple of different things, but the key ones are it is continuous and differentiable pretty much at all points. In other words, we don't have a graph. This would be a discontinuous graph. There's an empty space there. If you're dealing with a function that has an empty space like that, you cannot do the trick we're about to do. If you have a function that looks like this point right here is actually non-differentiable. I'm not going to go into the details on that, but if you have a really sharp edge like that, then this technique also won't work. In physics, we mostly ignore that because very rarely do we actually end up with functions that look like this. If this were a position versus time function, for instance, we don't have something that is at x equals 1 at one moment, and then without occupying the space in between it, it's suddenly at x equals 2. For me to do that, you had to see me move through those spaces between them. Obvious exceptions to this are things with quantum mechanics, but we're definitely not doing anything with that yet. Baby steps. In the real world, in the physical universe that we're dealing with right now, you don't really have a lot of instances where things just cease to exist somewhere and suddenly exist somewhere else, which means pretty much real functions are continuous pretty much all the time. In differentiable, I never have something that immediately changes from one thing to another. Usually, even if it's a really sharp change, there's a bit of a curve there. In short, when you're dealing with real-life functions, things that describe real things, they're pretty much most likely going to be continuous and differentiable, and they pretty much will be for anything that we work with here in class. Because of that, bad board. Because of that, we can actually treat this like a fraction. Now, for many of you, that was probably just a whole side thing, but I've got to make certain that I'm very specific about, hey, this is a bit of a stretch in mathematical terms, but when you apply it in the physical universe, it's not that big of a stretch at all, and this is what we'll do on a regular basis. So I'm going to pick up with this and rewrite this. We had dy equals 36x plus 4 dx. What this is saying is a very tiny piece of y, an infinitely small piece of y, would be equal to an infinitely small piece of x times these values. This would have been our slope. This is not actually the slope of the graph I keep using here. This is a crazy one just so we can kind of see what we're looking at. But that's what this is actually setting up. This is a relationship between what's happening in the y and what's happening in the x. I'm going to rewrite this a little bit more. dy equals 36x dx plus 4 dx. Here's what I want to do. I don't want to find an infinitely small piece of y. I want to know what y itself is, or more accurately, was. So here's what I'm going to do. We're going to add up all the little tiny pieces of y. So we're going to change this from dy into y by integrating them. And I'm going to integrate both sides. Now I want to stop on this for just a moment because the first time I showed students this, they said, oh, okay, it's the same, whatever I do on one side, I have to do on the other, so if I integrate over here, I integrate over here. That's not what's happening here. I do want to emphasize that. Y and x have a direct relationship to one another. Going back to my crazy town graph, dy and dx. As we shrunk dx down, dy shrunk down too. So if I'm doing the opposite, if I'm integrating one of them, dy, that's me going from the infinitely small and adding them back up to a finite interval, a finite space. I'm going from an infinitely small dot to all of the y. Well, if I do that, if I'm spreading this out from infinitely small back to a finite interval, this one, because they're directly related, x has to go from an infinitely small piece to a finite interval as well. Remember, the derivative had us shrinking these down, and now the integral, if I integrate one of them, the other, because it's related, will need to also do something very similar. So, just because you integrate one side of a thing doesn't mean you have to integrate the other, but in this case, if I want to add up all of my pieces of dy, since it is directly related to x, x must also be integrated as we expand those out to a finite interval. Well, if I integrate dy, that's just adding up all my little pieces of y, and I end up with basically y. I'm going to do this as a hand-wavy indefinite integral. Technically, I need either limits of integration or I would add a constant, but that constant could then subtract over to the other side. Right now, I'm trying to find y. Okay, well, I can look at the integral of this. Integral is basically undoing what a derivative does. So what you could imagine is this: when I integrate it, it's going to be, let's say that we've got a constant here, and here's our x and dx. Well, we know for the derivative, we would have some constant times x raised to a number, and then we would then get the constant divided by number times x raised to the number minus 1. We're actually going to do the exact opposite of that. So this is derivative. For an integral, technically this is what we would call an antiderivative, but it's undoing that. So if I end up with constant times x raised to the number, then we end up with, when we integrate it, the constant divided by number plus 1 times x raised to the number plus 1. If I take the derivative of this, then that becomes number minus 1, and I would divide it by number, multiply it by that, you'll find that you'll get the constant times x times number. Maybe a little difficult to follow, but see what happens here. This will go from x to the first to x squared. So when I integrate this first term will actually become x squared. But then I would divide by number plus 1, which is 2, so that's 36 divided by 2, which is 18. Plus, my next term is 4 times x to the 0, that'd be 4 divided by 1 times x raised to the 1, which is just, well, x, and that's just 4. Plus, here's where the indefinite integral comes in, because whenever you integrate it, there could have been a constant that when you take the derivative, it goes to 0. Now, sometimes there's a constant, sometimes there isn't. You would usually have to fit boundary conditions, but what I want you to see is this: 18x squared plus 4x plus some constant, we are getting back the very thing that we started with, which is 18x squared plus 4x, and my constant is 6. Now, in order to find that constant, I may need some additional information. All right. Now that we've got just a rudimentary understanding of how to go through and do some integration, let's actually apply this. Now, what I'm about to do is a rough derivation of the kinematic equations. This is not the thorough, fully mathematic way of doing it, but it's a good way to actually get you set up, and for the purposes of our class, it's good enough for what we're actually looking for. You'll see where the equations come from, and if you would have to on the AP exam, for instance, you could go through and you could derive equations very similar to this. Now I'm going to get us set up for that in just a moment.